A rocket ascends from Cape Canaveral, its engines carving fire into the morning sky. Inside it, a small metal traveler no bigger than a car, carrying the dreams of an entire planet. Its name, Voyager 1. A machine built not for war or conquest, but for curiosity. Humanity's message in a bottle cast into the vast cosmic ocean. As we speak, it still drifts, more than 22 billion kilometers from Earth. Its faint signal, weaker than a whisper, still reaches us through the static of deep space. Every few seconds, another photon returns home, carrying proof that Voyager still endures. It is the farthest object humanity has ever sent into the universe. A single creation that has outlived the generation that launched it, and will outlast the species that made it. Decade after decade, it has moved farther from the sun, crossing invisible frontiers we once believed unreachable. But before we journey deeper into this story, there's something important to understand. This documentary is not fiction, nor is it fully generated by artificial intelligence. Every concept and event you'll hear in this narration is based on verified peer-reviewed science, carefully examined and interpreted for clarity. Some of the visuals you'll see are artistically generated to help illustrate complex ideas. Think of them not as imagination, but as visualization, a bridge between what science understands and what we are still discovering. And if you find value in these explorations, thoughtful science told with care, a quick subscribe helps us continue creating more journeys like this one. Now imagine this. It has been nearly half a century since Voyager 1 left our world. 5 decades of silence, 5 decades of distance, 5 decades of a journey no human eye has seen, but every human heart somehow feels. And yet this story does not end with us, because Voyager 1 is still traveling, and it will keep traveling long after our cities crumble, our oceans shift, and our sun fades. This is not just the story of a spacecraft, it is the story of time itself, a journey through millions, even billions of years. A voyage beyond the solar system, beyond the Milky Way, and eventually, beyond everything we know. This is Voyager 1, the eternal journey beyond time. The year 1977 represents a unique moment in human history, a brief window when our technological capability aligned with our cosmic ambition. The space age was less than 20 years old, but already we had walked on the moon and sent robotic emissaries to several planets. The twin Voyager missions represented the culmination of this early space era's audacity and optimism. The planetary alignment that made the Voyager missions possible occurs only once every 176 years. In the late 1960s and early 1970s, NASA scientists recognized that the outer planets, Jupiter, Saturn, Uranus, and Neptune, would align in such a way that a spacecraft could use gravitational assists to visit all 4 worlds in a single grand tour. This configuration, sometimes called the Grand Tour alignment, presented an opportunity that would not come again until the middle of the 22nd century. Voyager 2 actually launched first, on August 20, 1977, from Cape Canaveral. Despite its numerical designation, it was designed to take the longer route, visiting all 4 giant planets. Voyager 1 followed 16 days later, on September 5, 1977, carrying identical instruments but taking a faster trajectory that would carry it to Jupiter and Saturn before ejecting it from the plane of the solar system. The launch itself was spectacular. A Titan 50 Centaur rocket, one of the most powerful available at the time, roaring to life in the late summer heat of Florida. The rocket's first stage burned for just over 2 minutes, consuming 158,000 kilograms of propellant, to lift the vehicle clear of Earth's densest atmosphere. The second stage ignited at an altitude of 52 kilometers, burning for nearly 2.5 minutes. Finally, the Centaur upper stage executed 2 burns, first placing the spacecraft into Earth orbit, then firing again to accelerate it to escape. Velocity, the speed necessary to break free of Earth's gravitational embrace forever, as Voyager 1 separated from its launch vehicle and oriented itself toward the outer solar system. It became, in that moment, something more than a machine. It became a traveler, an explorer, an ambassador. Its suite of scientific instruments powered up, magnetometers to measure magnetic fields, plasma detectors to analyze charged particles, cosmic ray detectors to study high-energy radiation, and cameras, the cameras, capable of capturing images that would transform our understanding of the solar system. The journey to Jupiter took 18 months. During that time, Voyager 1 continued its instrument calibrations and sent back regular status reports. The spacecraft was monitored by NASA's Deep Space Network, an array of massive radio antennas positioned around Earth at Goldstone, California, Madrid, Spain, and Canberra, Australia, ensuring that at least one antenna could always communicate with the probe regardless of Earth's rotation. On March 5, 1979, Voyager 1 made its closest approach to Jupiter, passing within 278,000 kilometers the giant planet's turbulent cloud tops. What it revealed astonished even the most optimistic scientists. Jupiter's famous Great Red Spot, a storm that had been observed from Earth for at least 300 years, appeared in unprecedented detail. This enormous anticyclonic storm, large enough to swallow 2 or 3 Earths, rotates counterclockwise with winds exceeding 400 kilometers per hour at its edges. Voyager's images revealed intricate spiral structures within the storm, smaller eddies being absorbed and torn apart, a vast atmospheric engine powered by heat rising from Jupiter's interior. But the Great Red Spot was merely one of many discoveries. Voyager 1 revealed that Jupiter's atmosphere was far more active and complex than anyone had imagined, with multiple jet streams, dozens of smaller storms, and a banded structure that reflected deep convection patterns. The spacecraft discovered active volcanism on Io, Jupiter's innermost large moon, the first volcanic activity ever observed on a world beyond Earth. Volcanologist Linda Morabito discovered the first volcanic plume in a Voyager image, a plume rising more than 280 kilometers above Io's sulfurous surface. This finding revolutionized our understanding of planetary geology, demonstrating that small worlds far from the Sun could possess active interiors heated by tidal forces from their parent planet. Europa, another of Jupiter's major moons, revealed a surface entirely unlike Io's. Instead of volcanoes, Europa displayed a cracked, icy crust with very few impact craters, suggesting a young, perhaps geologically active surface. Though Voyager's instruments could not peer beneath that ice, the images planted seeds of speculation that would grow over subsequent decades. Could liquid water exist beneath Europa's frozen shell? Could life have emerged in those dark oceans? 9 months after the Jupiter encounter, on November 12, 1980, Voyager 1 reached Saturn. The ringed planet had been observed through telescopes for centuries. Galileo first noted its strange handles in 1610, though his primitive telescope couldn't resolve them into rings. Christian Huygens correctly identified the ring structure in 1655, but no Earth-based telescope, no matter how powerful, could prepare astronomers for Voyager's revelations. Saturn's rings are not the simple, elegant structures they appear from Earth. They are impossibly complex, thousands of individual ringlets, gaps, waves, and kinks produced by gravitational interactions with Saturn's numerous moons. The rings are remarkably thin, typically just 10 to 100 meters thick, yet they span more than 280,000 kilometers from end to end. They consist primarily of water ice, with particles ranging from grain-sized fragments to house-sized boulders, each independently orbiting Saturn. Voyager 1 discovered intricate structure in Saturn's atmosphere as well, though less dramatic than Jupiter's. The planet's butterscotch color comes from ammonia crystals and other compounds in its upper atmosphere. Wind speeds on Saturn exceed 1,800 kilometers per hour, the fastest in the solar system. The spacecraft studied Saturn's magnetosphere, discovering that it was shaped by interaction with the solar wind into a long, comet-like tail stretching millions of kilometers downstream. But perhaps the most scientifically significant aspect of the Saturn encounter was Voyager 1's close approach to Titan, Saturn's largest moon and the only moon in the solar system with a thick atmosphere. The spacecraft passed within 6,490 kilometers of Titan's cloud tops, peering through the hazy orange atmosphere with its instruments. While the cameras could not penetrate the thick haze to see the surface, other instruments revealed that Titan's atmosphere is primarily nitrogen, like Earth's, with significant amounts of methane and complex organic molecules. Surface pressure appeared to be about 1.5 times Earth's, and the temperature hovered around 179 degrees Celsius. The Titan encounter sealed Voyager 1's fate and its destiny. To achieve the close approach necessary for detailed study of this intriguing moon, the spacecraft had to adopt a trajectory that carried it sharply northward above the plane of the solar system. This maneuver, while scientifically invaluable, meant that Voyager 1 would never encounter another planet. Its mission to explore the outer planets was complete. But before turning away from the inner solar system forever, Voyager 1 had one more task to perform, one that would produce arguably the most philosophically significant image in human history. On February 14, 1990, nearly 13 years after launch, Voyager 1 was 6 billion kilometers from home, beyond the orbit of Neptune. At the request of Carl Sagan, NASA commanded the spacecraft to turn its camera back toward the inner solar system one final time. It was a risky maneuver. Pointing the camera toward the sun risked damaging the sensitive instruments with direct solar exposure. But the operators were careful, and over the course of several hours, Voyager captured 60 images that would be assembled into a mosaic, a family portrait of the solar system. In one of those images, captured from that enormous distance, Earth appears as it truly is in the cosmic context, a pale blue dot, barely a single pixel in size, suspended in a beam of scattered sunlight. The image is humbling in a way that words struggle to capture. Everything that has ever happened in human history, every war, every love affair, every discovery and disaster, every birth and death occurred on that tiny point of light. Lost in the vastness, Carl Sagan would later write about this image. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. On a mote of dust suspended in a sunbeam. After capturing this final glimpse of home, Voyager 1's cameras were shut down permanently. Power was limited and would only become more so with time. The plutonium-238 in the spacecraft's radioisotope thermoelectric generators, RTGs, was decaying, producing less heat with each passing year, and thus less electricity. Systems had to be prioritized. The cameras, having completed their primary mission, were deemed less essential than other instruments that could continue studying the interstellar environment. In that moment, as the cameras powered down for the last time, something shifted. Voyager 1 was no longer an observer in the traditional sense. It could no longer see, no longer capture images of the universe through which it traveled. It became, instead, something more like a monk in deep meditation, sensing the environment through other means, feeling the solar wind with its plasma detectors, tasting cosmic rays with its high-energy particle instruments, but no longer looking back. As Voyager turned away, Earth became nothing more than a memory a single pixel of light lost in eternity. Time stretches forward now beyond the scope of recorded history, beyond the lifespan of civilizations, into a deep future where the present becomes ancient history, and then myth, and then nothing at all. 40,000 years. It is a span that dwarfs all of human civilization. When we look back 40,000 years from our present moment, we see a world before agriculture, before cities, before writing. We see humans living in small bands, creating the first sophisticated art, the cave paintings of Chauvet and Altamira that still move us today. We see a world with more human diversity than our modern era. Homo sapiens shared the planet with Neanderthals and Denisovans, other branches of the human family that would not survive to see the present. Now project that same span forward. What will Earth look like 40,000 years from now? The land masses will have shifted, though not dramatically. Tectonic plates move at roughly the speed of fingernail growth, a few centimeters per year. Over 40 millennia, the Atlantic Ocean will have widened by perhaps 1.5 kilometers. Australia will have drifted another 1.5 kilometers northward, and the African continent will have continued its slow collision with Europe, further building the Alps and Mediterranean mountain ranges. Coastlines, however, may have changed significantly, depending on Earth's climate trajectory. Will our species have successfully stabilized atmospheric carbon dioxide, or will we have allowed runaway warming to melt the ice sheets? Will sea levels have risen by meters or tens of meters? Will cities like New York, London, Shanghai, and Mumbai lie beneath the waves, their ruins hosting entirely new ecosystems? The biological world will have continued its relentless evolution. Species alive today may have given rise to descendants so altered that they would be classified as entirely new species. Others, possibly many others, will have gone extinct, their genetic lineages terminated by climate change, habitat loss, disease, or simple bad luck. If humanity still exists in recognizable form, we will have continued evolving as well, though predicting the direction of human evolution is fraught with uncertainty. Will we have merged with our technology, becoming something post-human? Will we have spread to other worlds? Or will we, like so many species before us, have vanished, leaving only our artifacts as evidence that we once existed? The night sky will have changed. Stars have their own motion through the galaxy, called proper motion, and over 40,000 years, the constellations we know will have shifted noticeably. The Big Dipper will be stretched and distorted. Orion's belt will have loosened. New stars will have entered our neighborhood, while others will have drifted away. The North Star, Polaris, will have precessed away from Earth's rotational axis. We will be pointing at a different star altogether. And somewhere in this transformed cosmos, still traveling at 17 kilometers per second, Voyager 1 continues its journey. 40,000 years from now, around the year 42,025 CE, Voyager 1 passes within 1.6 light-years of the star Gliese 445, currently located in the constellation Camelopardalis. This will be the closest stellar approach Voyager 1 will make for many millennia afterward. For perspective, Gliese 445 is a red dwarf star, much smaller and dimmer than our Sun, but still a fusion furnace converting hydrogen to helium in its core, still warming any planets that might orbit it. Let us imagine this moment. Voyager drifts through the darkness, its hull pitted by 40,000 years of micrometeorite impacts. Interstellar dust grains, though incredibly sparse, still exist in the void between stars, and at Voyager's speed, even the tiniest particle strikes with considerable energy. The spacecraft's distinctive golden antenna dish may be cratered and scarred. The gold plating on the Golden Record, however, remains largely intact. Gold is remarkably resistant to corrosion and radiation damage, chosen specifically for its durability. The spacecraft's power is long since depleted. The RTGs that once generated over 400 watts of electricity at launch were producing less than 250 watts by the 2020s. By the 2030s, NASA engineers will have to shut down the remaining scientific instruments one by one as power levels drop below operational thresholds. Sometime around 2036, give or take a few years, the last instrument will fall silent. After that, there will be no more telemetry, no more signals, no more communication with the civilization that built it. But silence does not mean death, not for a spacecraft in the vacuum of space. There is nothing to corrode it, no air to create rust, no water to seep into its electronics. Voyager simply continues. Its velocity remains essentially unchanged. There is no friction in space to slow it down. Newton's first law holds absolute sway. An object in motion remains in motion. Voyager's trajectory will curve slightly as it passes through various gravitational fields, but these deflections are minor. The spacecraft is effectively a new planet in its own right, a tiny world with a permanent orbit around the galactic center, a period of roughly 225 million years. As Voyager passes near Gliese 445, the red dwarf's dim light falls upon the spacecraft's surfaces, perhaps warming them slightly above the background temperature of space. That background temperature is not zero. It is about 2.7 Kelvin, or 270.45 degrees Celsius, the residual heat from the Big Bang itself, now cooled by 13.8 billion years of cosmic expansion. This is the temperature to which Voyager's hull has slowly equilibrated, making the spacecraft one of the coldest objects in the galaxy. The golden record, mounted on the exterior of the spacecraft, still glints faintly in the starlight. Its cover is etched with instructions for playing it, diagrams showing the stylus placement, the rotation speed, the method for decoding the images. These instructions are predicated on certain assumptions: that whoever finds the record understands binary notation, that they can interpret scientific symbols, that they possess a curiosity about the object's contents and a desire to decode its message. What message would they find if they somehow retrieved and played it? They would hear greetings, "Hello from the children of planet Earth" in English, "Assalamu alaikum" in Arabic, "Namaste" in Hindi, 55 languages in total, representing the diversity of human culture, though as critics noted at the time, weighted heavily toward languages spoken in 1977 and inevitably leaving many out. They would hear music, Bach's Brandenburg Concerto No. 2, Chuck Berry's Johnny B. Good, a Javanese gamelan performance, a Navajo night chant, Beethoven's Fifth Symphony, and dozens of other pieces selected to represent the breadth of human musical expression. They would hear natural sounds, thunder, surf, birds, whale songs, the sound of a human heartbeat. They would hear human-made sounds, a train, a tractor, Morse code, the voice of then Secretary General of the United Nations Kurt Waldheim offering formal greetings. And if they could decode the images, 116 photographs encoded in analog format, they would see mathematical definitions, the solar system's location in the galaxy, the structure of DNA, human anatomy, pictures of people from various cultures, images of animals and plants, photographs of architecture and technology, pictures of landscapes and seascapes. It is a message of extraordinary ambition and inevitable inadequacy. How do you summarize an entire planet, an entire species, in 90 minutes of audio and 116 images? What do you include? What do you leave out? The Voyager team made their choices, and those choices now travel through space as the de facto representation of humanity, whether we endorse them or not. But 40,000 years from now, does any of this matter? Will humanity still exist? Will we remember that we launched this probe? Will we care? Perhaps humanity will have transcended our biological origins, uploading our consciousness into digital substrates, spreading through the galaxy as information rather than flesh. Perhaps we will have encountered other intelligences and the Voyager record will seem quaint, a historical curiosity from our lonely, isolated age. Perhaps we will have destroyed ourselves in nuclear war, or engineered a plague we couldn't control, or succumbed to runaway climate change. And Earth will be a planet recovering from the Anthropocene, its ecosystems rebuilding without us. Or perhaps, and this is both the most mundane and most optimistic possibility, humanity will still be here, still looking up at the stars, still telling stories about the machines we sent into the darkness. Children in 2025 CE might learn about Voyager in school, much as children today learn about ancient explorers. The spacecraft might be to them what the Phoenician traders or the Polynesian voyagers are to us. Distant ancestors who ventured into the unknown with primitive technology and enormous courage, but Voyager itself knows none of this. It has no awareness, no sense of its significance. It is simply matter arranged in a particular configuration, following the laws of physics through the void. The poetry is not in the machine, but in what it represents, the fact that we, a species that emerged from African grasslands only a few 100,000 years ago, managed to fling a piece of ourselves into the cosmos, that we attached to it not just instruments and computers, but music and greetings and pictures, a message that says, we were here, we existed, we reached out. Long after our voices fade, Voyager still sings. The number is almost meaningless to human cognition. We can write it, we can say it, but we cannot truly feel what it means. All of recorded history, from the first Sumerian cuneiform tablets to the present moment, spans less than 6,000 years. 1,000,000 years is more than 160 times that entire span. It is a temporal chasm so vast that trying to peer across it makes the mind reel. Yet the universe treats 1,000,000 years as barely a moment. Stars live for millions, billions, even trillions of years. Galaxies persist for cosmological timescales that dwarf even stellar lifetimes. And in this context, Voyager's 1,000,000-year mark is just another milestone in a journey that will continue for eons. 1,000,000 years from launch places us in approximately the year 1177 CE. Earth, our pale blue dot, has continued evolving. The continents have shifted noticeably now, perhaps 50 kilometers from their current positions, enough to slightly alter ocean currents and global climate patterns. The tectonic forces that have been building the Himalayas continue their work. The mountains may be several kilometers higher, though erosion works against this uplift. Antarctica, depending on Earth's climate history over the intervening millennia, may have shifted slightly, perhaps enough to alter the circumpolar current that keeps it so cold. Ice ages have come and gone, assuming humanity hasn't disrupted the Milankovitch cycles that drive Earth's long-term climate oscillations. These cycles, changes in Earth's orbital eccentricity, axial tilt, and precession, operate on timescales of tens of thousands to hundreds of thousands of years. Over 1,000,000 years, Earth will have experienced multiple glacial and interglacial periods, with ice sheets advancing and retreating, sea levels falling and rising by hundreds of feet. The biological consequences are difficult to predict, but certain to be profound. 1,000,000 years is ample time for significant evolution. Modern humans, Homo sapiens, emerged as a distinct species only about 300,000 years ago. 3 times that span has now elapsed. If any descendants of humanity still exist, they may be so changed that we would not recognize them as the same species. Or perhaps Homo sapiens is extinct, replaced by successor species, whether biological descendants, synthetic intelligences we created, or some hybrid form we cannot presently imagine. Many species alive in 1977 are certainly gone. The average species lifespan varies enormously, but for mammals, it's typically 1 to 2 million years. Some species alive at Voyager's launch will have evolved into descendant forms. Others will have left no descendants at all, their genetic lineages terminated. New species will have radiated into available ecological niches. The tree of life continues to branch, though which branches survive and which are pruned is always a matter of contingency and chance. And what of human artifacts? Cities built in the 20th century will be long gone, their ruins weathered beyond recognition or buried under sediment. Even our most durable constructions, stone monuments, concrete dams, tunnel systems, will show serious degradation after 1,000,000 years. Future geologists might find a thin layer in Earth's stratigraphy that contains anomalous concentrations of plastics, metals, and radionuclides, a signature of the Anthropocene, a testament that something unusual happened on Earth in the late Holocene epoch. But in the deep freeze of space, far from Earth's active geology and corrosive atmosphere, Voyager 1 persists in better condition than anything left behind on our planet. The spacecraft has traveled approximately 17 trillion kilometers, about 1/800 light-years. To put this in perspective, Voyager has crossed roughly 1.8% of the distance to the galactic center, which lies about 26,000 light-years away. More significantly, Voyager is now fully immersed in interstellar space, a transition it first made in August 2012 when it crossed the heliopause, the boundary where the solar wind's influence gives way to the interstellar medium. But even interstellar space is not uniform. The Sun moves through different regions of the galaxy, carrying its heliosphere with it, and that movement takes it through clouds of varying density and composition. 1,000,000 years into its journey, Voyager 1 passes through the Oort cloud, or rather, through the region where the Oort cloud is theorized to exist. This enormous spherical shell of icy bodies surrounds the Sun at a distance of roughly 2,000 to 100,000 astronomical units, AU. For reference, Neptune, the most distant planet, orbits at about 30 AU. The Oort cloud is thus mind-bogglingly vast, extending a significant fraction of the way to the nearest stars. The Oort cloud has never been directly observed. Its existence is inferred from the long-period comets that occasionally plunge into the inner solar system, apparently disturbed from distant orbits by gravitational perturbations. These icy bodies are thought to be the remnants of the solar system's formation, planetesimals that were flung outward by gravitational interactions with the giant planets and now orbit in a tenuous halo around the Sun. The density of objects in the Oort cloud is extraordinarily low, perhaps one comet-sized body per cubic astronomical unit. Space, as Douglas Adams famously noted, is big, really big. Voyager could pass through the Oort cloud for thousands of years without coming anywhere near one of these distant ice balls. The spacecraft would simply continue its trajectory, surrounded by the profound darkness that characterizes this region. And it is dark here, unimaginably dark. The Sun from the inner edge of the Oort cloud is just another star, brighter than the others, but no longer the dominant source of light. From the outer edge of the Oort cloud, the Sun is merely a bright point, providing no more warmth than any other nearby star. There are no planets visible, no landmarks, nothing to indicate that this region belongs to any particular stellar system. It is the ultimate frontier, the boundary between the Sun's domain and the true interstellar void. Yet even here, Voyager carries its message. The golden record remains sealed, its contents preserved by the vacuum and cold. The instructions on its cover have not faded. There is nothing in space to fade them. The images and sounds encoded on its surface wait, patient in a way that only inanimate objects can be patient. Consider what the record contains: the sound of surf breaking on a shore. In 1,000,000 years, how many shores will have eroded away? How many coastlines will have been submerged or uplifted? The recording captures a moment, a particular wave, breaking on a particular beach, on a particular day in the 1970s. That wave is gone, dissipated back into the ocean within seconds of its recording. The beach may be gone too, perhaps drowned by rising seas or thrust upward by tectonic forces. But the sound persists, encoded in gold, traveling through the darkness. The record includes a recording of a human heartbeat, a young woman named Anne Druyan, who would later marry Carl Sagan. In the minute captured on the record, her heart beat perhaps 60 times. She was thinking about humanity's history and future, trying to encode her brainwaves and emotions into the measurement, though whether such things can be captured through heart rhythms is doubtful. But the attempt itself is poignant. She offered her heartbeat as a symbol of life, of biological existence, of the particular way that complex chemistry can organize itself into something that maintains homeostasis, reproduces, evolves. A million years later, is there still a heartbeat anywhere in the universe that sounds like that? Are there still humans, or any biological organisms, whose hearts beat in roughly that rhythm, pushing oxygenated blood through a circulatory system? Or has life moved beyond such mechanisms, achieving consciousness through entirely different means? These questions are unanswerable, both in the sense that we cannot predict the future and in the more profound sense that Voyager cannot answer them. The spacecraft is deaf and blind now, unable to sense its environment except through the most basic physical principles. It cannot look back to see whether Earth still exists, cannot turn its antenna homeward to listen for radio signals. It simply continues, a fossil of technology from a particular moment in one species' development. Yet calling it a fossil doesn't fully capture what Voyager represents. Fossils are remnants, the remains of something that once lived. Voyager was never alive, yet it carries life's message. It is more like a thought that a species had about itself, about its place in the cosmos, about its desire to reach beyond its own limitations. And thoughts, once articulated, take on a kind of existence independent of the thinker. Even if humanity vanishes, even if Earth becomes sterile, this thought, this small collection of images and sounds and mathematical symbols, will continue traveling through space, existing as a fact about the universe, a pattern of matter that has meaning. Even if there is no longer anyone to understand that meaning, the profound silence of the Oort cloud mirrors the silence that has fallen over Voyager itself. No electricity flows through its circuits. No data moves through its computers. The spacecraft is cold, colder than any deep freeze on Earth could achieve, thermally equilibrated with the cosmic microwave background radiation that pervades all of space. In this frozen state, it is preserved against decay. There is no rust here, no rot, no weathering. Time's arrow still points forward. Entropy still increases, but the processes are glacially slow. Micrometeorite impacts continue, but they are rare. Cosmic rays pass through the spacecraft structure, very slowly damaging the atomic lattices of its metals and plastics. But these effects accumulate gradually over geological time. The Golden Record's gold plating may have acquired a thin layer of surface contamination from interstellar dust, but gold is largely immune to chemical reactions. It does not oxidize, does not corrode. The record could remain playable for billions of years, assuming someone or something finds it and has the means to decode its contents. 1 million years have passed, and still it travels, alone, unblinking, unstoppable. 100 million years. We have now entered timescales that are geological, even on cosmic standards. This is the timescale on which continents drift across oceans, on which mountain ranges rise and erode away entirely, on which impact craters, even large ones, can be obliterated by tectonic activity and weathering. On Earth, 100 million years ago, dinosaurs dominated the Cretaceous landscape. The great extinction event that would end their reign was still 34 million years in the future. Flowering plants were just beginning their explosive radiation that would come to dominate terrestrial ecosystems. The Atlantic Ocean was narrower. India was a large island moving northward toward its collision with Asia. The Rockies had not yet formed. Project that same span forward from 1977, and we arrive at roughly the year 100,177 CE. Earth's continents have moved dramatically. The Atlantic has widened by perhaps 5,000 kilometers, roughly its current width. The Mediterranean Sea may have closed entirely as Africa continues pushing into Europe. Australia might have collided with Southeast Asia. The Great Rift Valley in Africa, currently pulling the continent apart, might have opened into a new ocean. Coastal California might have become an island chain as the Pacific Plate continues grinding past the North American Plate. The biological transformation is total. Every species alive in 1977 is either extinct or evolved into forms so different that taxonomists would classify them as new species. This is roughly the timescale on which new orders and families of organisms emerge. The mammals that exist 100 million years from now may be as different from today's mammals as modern mammals are from their Cretaceous ancestors. Small, probably nocturnal creatures that lived in the shadows of dinosaurs. What of humanity? The question seems almost absurd at this timescale. The entire genus Homo is only about 2.8 million years old. The oldest hominins, the lineage that eventually led to humans, emerged only about 6 to 7 million years ago. 100 million years is more than 14 times the entire history of the hominin lineage. If any trace of humanity survives this long, it would be in forms so changed that the concept of human would be meaningless. Perhaps our descendants, biological or otherwise, have spread through the galaxy. Perhaps we vanished within the first few thousand years of our spacefaring age. Perhaps Earth was struck by an asteroid that sterilized all complex life, and the planet had to begin the process of biological diversification again from whatever survived in the deep ocean or subsurface. And still, Voyager 1 continues its journey. The spacecraft has now traveled approximately 1.7 million light-years, roughly 16 trillion kilometers. This is a distance that begins to be cosmologically significant. For comparison, the Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 2.5 million light-years distant. Voyager has traveled roughly 2/3 of the way to Andromeda, though it is not aimed in that direction. More significantly, Voyager 1 has made considerable progress through the Orion arm of the Milky Way, the spiral arm that contains our solar system. Our galaxy is a barred spiral with several major arms: Perseus, Norma, Scutum Centaurus, and others. The Orion arm, also called the Orion spur, is actually a minor arm, a small branch connecting the Sagittarius and Perseus arms. It contains the Sun, Sirius, Procyon, and many other stars visible from Earth. As Voyager drifts through this region, the stellar environment around it slowly changes. Stars are born and die. Massive stars which burn through their nuclear fuel in mere millions of years have already gone through their entire life cycles many times over. Some have exploded as supernovae, enriching the interstellar medium with heavy elements forged in their cores. Others have collapsed into neutron stars or black holes, exotic remnants compressed to unimaginable densities. Voyager may have passed relatively near some of these stellar explosions. When a massive star goes supernova, it briefly outshines an entire galaxy, releasing as much energy in a few weeks as the Sun will emit over its entire 10 billion year lifetime. The explosion sends a blast wave of hot plasma racing outward at a significant fraction of light speed, sweeping up interstellar gas and dust and compressing it into glowing shells and filaments. If Voyager happened to be within a few light years of such an explosion, the effects could be significant. The intense radiation, gamma rays, X-rays, ultraviolet light, would blast the spacecraft's exterior. The materials would be heated, perhaps to temperatures of hundreds or even thousands of degrees. The Golden Record's cover might be warped or damaged. The spacecraft structure might be eroded. But even this is not destruction, not in the usual sense. Voyager has no life to lose, no function to maintain. It is already inert. The supernova would simply modify it, change its form slightly, add energy to its atoms, but the fundamental fact of its existence would persist. And then, in the centuries after the supernova, as the blast wave passed and the radiation faded, Voyager would cool again, returning to its equilibrium with the cosmic background. It would continue its trajectory, perhaps slightly altered by the force of the blast, scarred but persistent. In other regions, Voyager passes through nebulae, vast clouds of gas and dust that are both the remnants of dead stars and the nurseries of new ones. These nebulae are beautiful when viewed from a distance, like the famous images from Hubble or James Webb telescopes, intricate structures of glowing hydrogen, oxygen, and sulfur, sculpted into pillars and walls and arcs by stellar winds and radiation pressure. But from within a nebula, the view is less dramatic. The density is still extremely low by terrestrial standards. These clouds are better vacuums than anything we can create on Earth. Voyager would notice the increased density only as a slight increase in drag and micrometeorite impacts. The view would be one of gradually increasing haziness, a subtle dimming of distant stars as their light is scattered by dust grains. But nothing like the clouds in Earth's atmosphere. Some of these nebulae contain regions of active star formation. Within dense cores, gravity is pulling gas together, heating it through compression, eventually reaching temperatures and pressures high enough to ignite nuclear fusion. When this happens, a star is born, pushing back against its surrounding cocoon of gas with fierce radiation and stellar wind. These newborn stars often form in clusters, gravitationally bound groups of dozens, hundreds, or even thousands of stars that will gradually disperse over tens or hundreds of millions of years. Voyager might drift through one of these stellar nurseries, surrounded by proto-stars and young stars just beginning their long lives. The contrast is poignant. These stars, some of which will live for trillions of years, are just being born, while the star that gave rise to Voyager, our Sun, is middle-aged, halfway through its life cycle. The spacecraft is a messenger from an earlier generation of stars, carrying information about worlds that orbit an old yellow star, a star that will someday die. Throughout all of this, the golden record remains attached to Voyager's exterior, still containing its message. The record includes an image of the Sun's location in the galaxy, plotted using the positions of 14 pulsars, rapidly rotating neutron stars that emit regular pulses of radio waves. The idea was that any spacefaring civilization that found Voyager could use the pulsar map to determine where and when the spacecraft was launched. Pulsars slow down over time as they lose rotational energy, so their periods at any given time are diagnostic of the date. But 100 million years later, this map is degraded. Pulsars slow down, and their periods have changed significantly. Some of the 14 pulsars marked on the golden record may no longer exist. Their magnetic fields may have decayed to the point that they no longer emit detectable radiation. The map is not useless, but it is more difficult to interpret, requiring corrections for the pulsar's spin down. A sufficiently advanced civilization could still use it to determine Voyager's origin, but the message is no longer as clear as it once was, and who might that civilization be? Over 100 million years, could other intelligent species have emerged? On Earth, intelligence evolved once, in our lineage, though the exact path was contingent and might not repeat. Cephalopods display considerable intelligence, but they are limited by short lifespans and solitary lifestyles that prevent cultural transmission. Corvids and parrots show remarkable cognitive abilities, but lack the manipulative appendages and social structures that favored tool use in primates. Dolphins and whales are highly intelligent, but live in an environment where fire and metallurgy are impossible, blocking certain technological pathways. But the galaxy is vast, containing hundreds of billions of stars, many with planets, many of those planets potentially habitable. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy, but its parameters are deeply uncertain. We know that planets are common, that organic chemistry is widespread, but we have no idea how frequently life emerges, how often it becomes complex, how often intelligence evolves, or how long technological civilizations survive. Perhaps in these 100 million years, another species on another world orbiting another star has climbed the same ladder we did. Perhaps they looked up at their night sky with wonder. Perhaps they developed science, built telescopes, launched spacecraft. Perhaps one of their probes has passed near Voyager, two messages crossing in the darkness, like explorers from different civilizations meeting briefly on a remote trail before continuing their separate journeys. Or perhaps intelligence is vanishingly rare. Perhaps the circumstances that gave rise to human cognition, the particular sequence of climate changes, genetic mutations, and social pressures, are so specific that they occur only once in billions of years. Perhaps we are alone, and Voyager's journey is a soliloquy, a message that will never be heard. But the message continues anyway. This is perhaps the most profound aspect of the Voyager mission. It requires no response, no acknowledgement, no purpose beyond its own existence. It is expression for the sake of expression, meaning made tangible and set loose in the cosmos. The spacecraft passes through another region of the Orion Arm, through gravitational fields of stars that tug gently at its trajectory, through the subtle resistance of interstellar gas and dust, accumulating impacts, slowly eroding, yet fundamentally unchanged. It is still recognizable as what it was, a machine built by a technological civilization, carrying a message intended for someone or something else. It has become more than a machine. It is a fossil of consciousness, drifting between the ghosts of galaxies. This is the timescale of stellar evolution. The lifetime of stars like our Sun. We have now entered a temporal regime where not just biology and geology change, but the fundamental astrophysical context of our solar system. 5 billion years from now, around the year 501977 C, the Sun is dying. Our star is currently in the main sequence phase of its life, steadily fusing hydrogen into helium in its core. This process has been ongoing for about 4.6 billion years and will continue for roughly another 5 billion years. But nuclear fuel, even on stellar scales, is finite. Gradually, over the coming giga-years, billions of years, the Sun's core will accumulate helium ash from hydrogen fusion. This helium core will contract under its own gravity, heating up, while hydrogen fusion continues in a shell around it. This contraction causes the Sun to heat up and brighten. In fact, this process is already underway. The Sun is about 30% more luminous now than when it first formed. Over the next billion years, this brightening will accelerate. Eventually, perhaps a billion years from now, Earth's oceans will boil away. The planet will enter a runaway greenhouse state, similar to modern Venus, with surface temperatures hot enough to melt lead. Any life that has survived until this point will be extinguished, not by human-caused climate change, not by asteroid impact, not by nuclear war, but by the simple, inevitable evolution of the star that gave us life in the first place. But the Sun's transformation is only beginning. Around 5 billion years from now, the helium core contracts to the point that it ignites in a process called helium flash. Though for a star like the Sun, this is less of an explosion and more of a rapid adjustment. Helium begins fusing into carbon and oxygen, releasing enormous energy. The Sun enters the red giant phase, expanding dramatically. How dramatically? Models predict the Sun will eventually expand to somewhere between 200 and 300 times its current diameter. Its outer layers will reach the orbit of Earth, or possibly beyond. Mercury will be engulfed and vaporized. Venus will likely suffer the same fate. Earth's fate is less certain. Calculations are sensitive to assumptions about mass loss from the Sun and tidal effects. The planet might survive as a scorched, lifeless rock at the inner edge of the Sun's expanded envelope, or it might be consumed entirely, its atoms dispersed into the stellar atmosphere. Regardless of Earth's ultimate fate, the inner solar system is transformed beyond recognition. The habitable zone, the region where liquid water could exist on a planet's surface, has moved outward. Moons like Europa and Enceladus, previously frozen, might briefly have liquid water oceans, though whether this warmth lasts long enough for life to emerge is doubtful. Saturn's moon Titan, with its thick atmosphere and complex organic chemistry, might become almost Earth-like, at least for a geological moment. But this warmth is temporary. The red giant phase is unstable. The sun will pulsate, losing mass in powerful stellar winds. It will blow off its outer layers in a series of thermal pulses, eventually exposing its hot core. This remnant core, roughly Earth-sized but incredibly dense, is a white dwarf, the final state for stars like the Sun. The ejected outer layers form a planetary nebula, a beautiful but short-lived structure of glowing gas expanding into space. The white dwarf that was once our Sun will shine with residual heat, gradually cooling over trillions of years, eventually becoming a black dwarf, a cold, dark cinder, the ultimate endpoint of stellar evolution. But 5 billion years from now, we are just at the beginning of this transformation, with the Sun at its maximum size and brightness. And where is Voyager 1 during this apocalypse? The spacecraft is now approximately 85 million light-years from Earth, or rather, from where Earth used to be. At its constant velocity of 17 kilometers per second, about 61,000 kilometers per hour, Voyager has traveled an enormous distance, though still a tiny fraction of the observable universe, which has a radius of about 46.5 billion light-years. More significantly, Voyager is far beyond any danger from the Sun's red giant phase. The expanded Sun might engulf planets out to Earth's orbit or slightly beyond, but its influence on Voyager, which is hundreds of light-years away, is nil. The spacecraft does not see the Sun expand, does not feel its heat increase. In fact, Voyager cannot see the Sun at all in any meaningful sense. Its cameras are long dead, shut down 5 billion years ago, and even if they still functioned, the Sun would be just another star among many, indistinguishable from countless others, yet in a poetic sense. Voyager bears witness to its parent star's death. The spacecraft is a record, a testament to what existed during the Sun's middle age. It carries images of planets that might no longer exist, Jupiter's swirling clouds, Saturn's delicate rings. It carries sounds from Earth, a planet now potentially vaporized. It carries greetings in languages spoken by a species that is certainly extinct, possibly for billions of years. Consider the recordings of human voices on the Golden Record. When those recordings were made, the people speaking were alive, their brains generating thoughts, their vocal cords vibrating, their lungs expelling air. Those specific patterns of air pressure were transduced into electrical signals, then encoded onto a copper disc coated with gold. The people are now dead. This is guaranteed at 5 billion years. Not just dead, but decomposed, their atoms scattered, possibly integrated into other organisms, possibly locked in rock or dissolved in the ocean, assuming Earth still has an ocean, which by this point it almost certainly does not, but the pattern persists. The physical undulations in the Golden Record still encode those voices. If a being or device could read the record, those voices could be reconstructed, the pressure waves reproduced. In this sense, part of those people, the pattern of their voices, if not their consciousness or identity, still exists, traveling through space long after the atoms that made up their bodies have been dispersed and recombined countless times. The spacecraft itself has suffered 5 billion years of wear. Micrometeorite impacts have pitted its surface. Cosmic rays have slowly damaged its materials at the atomic level, creating defects in crystal structures, breaking molecular bonds. The Golden Record's surface, while remarkably durable, has accumulated a thin layer of interstellar dust and shows damage from radiation. Yet the record is likely still readable, assuming the technology and knowledge to do so. The Milky Way galaxy itself has changed significantly over these 5 billion years. Star formation continues, though at a declining rate as gas is consumed and stellar winds and supernovae blow material out of the galactic disk. The spiral structure shifts. Spiral arms are not fixed structures, but density waves, regions where stars and gas are temporarily compressed, triggering star formation. The pattern rotates at a different rate than the stars themselves, like a traffic jam that persists even though individual cars move through it. The galaxy has also been transformed by its gradual merger with Andromeda. This process began perhaps 4 billion years ago when the two galaxies first made a close passage. They are now in the process of coalescing, their gas clouds colliding, though individual stars almost never actually collide due to the vast distances between them, triggering massive bursts of star formation. The combined galaxy, sometimes called Milkomeda or Milkdromeda, is transforming into an elliptical galaxy, a more spherical distribution of stars lacking the elegant spiral structure of either progenitor. Voyager, launched from a planet orbiting a star in the Milky Way, is now adrift in Milkomeda. The night sky, if Voyager could see it, would be subtly different. The stellar density might be slightly higher or lower depending on the spacecraft's location in the merged galaxy. The central bulge might be larger and brighter, but these are subtle differences. To Voyager, one region of the galaxy is much like another, a vast darkness punctuated by distant points of light. And what of other intelligences? 5 billion years is an almost unimaginable span of time for biological evolution and technological development. If intelligent life is common, the galaxy might be filled with civilizations by now, some of them millions or billions of years more advanced than humanity was at its peak. Perhaps they have built structures at galactic scales, Dyson spheres around stars, megastructures channeling energy, perhaps even technologies that manipulate space-time itself, or perhaps intelligence is followed inevitably by extinction. Perhaps there is a great filter that prevents most civilizations from spreading beyond their home planets. Perhaps the challenges of interstellar travel are insurmountable, or perhaps advanced civilizations invariably destroy themselves through war, environmental collapse, or other catastrophes. Perhaps Voyager drifts through a galaxy that has been repeatedly seeded with intelligence, only to see each spark extinguished after a brief flare. But Voyager itself is proof that at least one species tried. We may have failed in 1,000 ways, we may have destroyed ourselves shortly after launching this probe, but we sent something out into the cosmos that declares, we existed. We were curious. We reached for the stars, the last witness to the age of the sun, carrying the sound of life from a world that no longer exists. 10 billion years after launch, we arrive at approximately the year 10,1,977 CE. This is twice the current age of the solar system. If our sun were a person, it would now be deceased for 5 billion years. In fact, by this point, the sun has long since passed through its red giant phase, shed its outer layers as a planetary nebula which has since dissipated, and now exists as a white dwarf, gradually cooling toward its final black dwarf state. Earth, if any trace of it remains, is a dead rock, either vaporized during the sun's expansion or left as a scorched cinder. Mars, the outer moons of Jupiter and Saturn, the Kuiper Belt, and the Oort cloud have all been baked by the sun's red giant phase. The solar system is no longer a system of planets, but a graveyard of worlds orbiting a slowly cooling stellar core. But the sun's death is only one small event in the galaxy's evolution. The more dramatic transformation is the completion of the Milky Way-Andromeda merger. This merger has been underway for billions of years by this point. The two galaxies first approached each other about 4-5 billion years into our timeline, drawn together by their mutual gravity. Their first passage was chaotic. Tidal forces stretched and distorted both galaxies, triggering enormous bursts of star formation as gas clouds collided and compressed. The galaxies swung past each other, then curved back, their trajectories bent by gravitational interaction. The second passage was more violent. By this time, significant amounts of gas and dust had been shocked and compressed, creating vast stellar nurseries. The cores of both galaxies, each containing supermassive black holes, the Milky Way is at about 4 million solar masses and Andromeda's at around 100–200 million solar masses, began their own orbital dance. Gradually, over billions of years, the two galaxies lose orbital energy, primarily through gravitational interactions with stars and gas, and settle into a single structure. The result is a giant elliptical galaxy, sometimes called Milkomeda, with a mass of roughly 1.5 trillion solar masses, the combined mass of both progenitors, minus whatever gas and stars were ejected during the merger. The spiral structures that characterized both the Milky Way and Andromeda are gone, replaced by a more uniform spherical distribution. Star formation has mostly ceased. Much of the gas was consumed during the merger, and what remains is too dispersed and hot to collapse into new stars. Milkomeda is entering the phase that characterizes most large elliptical galaxies, a slowly aging population of stars with little new birth. Voyager 1 is now somewhere in the outskirts of this giant elliptical galaxy. The spacecraft has traveled roughly 170 million light-years, a distance that begins to approach the scales between galaxies. In fact, depending on its exact trajectory and the outcome of the merger dynamics, Voyager might have been flung out of the galaxy entirely during the merger, joining the population of intergalactic stars, stars that orbit in the vast spaces between galaxies rather than within them. If Voyager remains within Milkomeda, it drifts through a galaxy profoundly different from the one it left. The Sun, its parent star, is no longer on the main sequence, no longer even a white dwarf but a cooling black dwarf. Though truly cold black dwarfs might not yet exist, they require longer than the current age of the universe to cool completely. The Sun is well on its way. Earth is gone, possibly vaporized, possibly ejected from the solar system during stellar encounters in the densely packed merger environment. Most stars in the galaxy are now old. The massive, bright blue stars that characterized star-forming regions have long since exploded or collapsed into neutron stars and black holes. The galaxy is dominated by red dwarfs, small, cool stars that burn their fuel parsimoniously, living for trillions of years. Many of these red dwarfs are accompanied by white dwarfs and neutron stars, the remnants of more massive companions. The galaxy is also darker. Fewer stars are being born, and many stars have already died. Luminosity, averaged across the galaxy, has declined. The bright spiral arms where young, hot stars once blazed with blue light are gone. What remains is a softer, redder glow, the light of old stars slowly exhausting their fuel. Yet even in this aged galaxy there might be life. Red dwarfs, though dim, are stable for trillions of years. Planets in close orbits around these stars could maintain liquid water on their surfaces for geological timescales far exceeding anything Earth experienced. Perhaps life has emerged on some of these worlds. Perhaps intelligence has evolved. Perhaps new civilizations are looking up at their night skies, studying their universes, asking the same questions we asked. Would they find Voyager? The probability is extraordinarily low. Space, even within a galaxy, is vast. Stars are separated by light years. The random chance of a spacecraft encountering another star system is vanishingly small. Current estimates suggest Voyager will not come within a light year of another star for tens of thousands of years at minimum, and the intervals between close approaches will only increase as the spacecraft penetrates deeper into interstellar space. But vanishingly small is not zero. Over 10 billion years with countless stars and potentially countless civilizations, someone might detect Voyager. Perhaps a civilization with advanced sensors detects its anomalous trajectory, a small object moving through space at a velocity inconsistent with natural astrophysical processes. Perhaps they investigate, send a probe to intercept it, recover it, study it. What would they find? A heavily damaged artifact, but likely still recognizable as artificial. The spacecraft's shape, the distinctive antenna dish, the RTG mounts, the instrument boom, is clearly not natural. The golden record, if it survives, is especially diagnostic, a flat, circular object with regular grooves covered with geometric diagrams and symbols. Any advanced civilization would recognize this as information storage, even if the specific medium is unfamiliar. If they decode the record, what would they make of its contents? The sounds of Earth, thunder, rain, wind, birds, whale songs, from a planet that no longer exists. Music in styles that no living being remembers. Images of a species called Homo sapiens, bipedal primates with complex language and tool use now extinct for billions of years. Greetings in 55 languages, none of which are spoken anymore, from a planet whose name is preserved only on this record. They would be archaeologists of the most profound sort, studying the only surviving record of an entire world, an entire ecosystem, an entire civilization. They might try to reconstruct Earth from the images and sounds. They might marvel at the diversity of life we shared our planet with. They might wonder what became of us, why we disappeared, whether our extinction was rapid or slow, violent or peaceful. But more likely, Voyager will not be found. It will simply continue its journey, a ghost ship traveling through an aging galaxy, carrying a message that will never be read, preserving memories of a world that has vanished, and still, the fact of its existence matters. Even if no one finds it, even if its message is never decoded, the golden record still contains those images, those sounds, those greetings. The pattern persists. In a universe governed by entropy, where everything tends toward disorder, this small collection of information, of order, of meaning, continues to exist. It has become what we could never be, eternal. A fossil not of bones but of thought, preserved in gold and electronics, drifting through a galaxy that has forgotten its creators. 100 billion years after launch brings us to the year 100 billion. 1,977 CE. We have now entered cosmological timescales, the timeframes over which the universe itself transforms. The universe is approximately 13.8 billion years old now in our present. 100 billion years from now, it will be roughly 114 billion years old, 8 times its current age. This is the timescale on which stellar evolution completes, on which galaxies finish their mergers, on which the structure of the cosmos becomes apparent. The most striking feature of this era is what it lacks: light. The universe is going dark. Star formation has essentially ceased. The process of making stars requires cold, dense gas clouds, and these clouds are becoming increasingly rare. Gas has been converted into stars, planets, and stellar remnants. Supernovae and stellar winds have heated much of the remaining gas, making it too hot to collapse. The merger of galaxies, like the Milky Way and Andromeda, has disrupted gas reservoirs and flung material out of galaxies entirely. By 100 billion years after the Big Bang, most galaxies have exhausted their star-forming gas. The galaxy formerly known as the Milky Way, now part of Milkomeda, or possibly merged into an even larger structure, contains primarily old stars and stellar remnants. The most massive stars, which burn bright but brief, are long since dead, having exploded as supernovae or collapsed into black holes. Mid-sized stars like the Sun have become white dwarfs, slowly cooling. Only the smallest stars, the red dwarfs, still fuse hydrogen in their cores. Red dwarfs have lifespans measured in trillions of years. A star with 1/10 of the Sun's mass can burn for more than 10 trillion years. But even these misers of nuclear fuel will eventually exhaust their hydrogen. In 100 billion years, the oldest and smallest red dwarfs are beginning to run low, transitioning into the blue dwarf phase, a theoretical stage where the star's outer layers contract making it temporarily hotter and bluer before finally settling into white dwarf retirement. The universe is also expanding, and the expansion is accelerating. This acceleration is driven by dark energy, a mysterious property of space itself that acts as a kind of anti-gravity. As the universe expands, the density of matter and radiation decreases, but dark energy density remains constant or possibly increases. This means dark energy's influence grows over time. The result is that galaxy clusters, gravitationally bound groups of galaxies, remain bound, but the spaces between clusters expand at an accelerating rate. Eventually, clusters become causally disconnected from each other. The space between them expands faster than light can cross it. From the perspective of an observer in one cluster, other clusters redshift into invisibility. Their light stretched to such long wavelengths that it becomes undetectable. Voyager 1, by this point, has traveled roughly 1.7 billion light-years from Earth's former location. This is a distance comparable to the separations between nearby galaxy clusters. Depending on the spacecraft's trajectory and the pattern of cosmic expansion, Voyager might be in the intergalactic void, the vast empty spaces between galaxies. These voids are not truly empty. They contain some gas, some stray stars, perhaps some intergalactic planets, but their density is extraordinarily low. The typical separation between objects might be hundreds of thousands or millions of light-years. Voyager could travel for billions of years without coming within a light-year of any star or galaxy. From this vantage point, if Voyager could observe its surroundings, the view would be one of profound darkness. Galaxies, once visible in all directions, have receded beyond detection. Only the nearest galaxies remain visible, perhaps Milkomeda itself, if Voyager has not traveled too far, or the local group remnant if those galaxies have merged into Milkomeda. But even these nearby galaxies are dim, their star formation long since ceased, their stellar populations aging and fading. The cosmic microwave background radiation, that faint echo of the Big Bang, has also faded. The universe's expansion has stretched this radiation from microwaves toward radio waves and beyond, reducing its temperature from the current 2.7 Kelvin to a fraction of a degree above absolute zero. Space is colder and darker than ever before. This is sometimes called the Great Silence, or the Degenerate Era, a time when the bright, active phase of the universe has ended, replaced by a slow, cold decline. The fireworks are over. Now comes the long, quiet dimming. Yet even in this darkness, Voyager persists. The spacecraft is now beyond ancient. Every material that composed it has been damaged by radiation, by micrometeorite impacts, by the sheer passage of time. The golden record's surface is scarred and pitted, though gold's chemical inertness means it has not corroded. The underlying information, the grooves encoding images and sounds, might still be partially recoverable, though decoding it would require sophisticated analysis and error correction. The spacecraft's structure might be fragmenting. After 100 billion years of micrometeorite impacts, some components might have been knocked loose. The antenna dish, once precisely shaped to transmit radio signals across billions of kilometers, might be warped or cracked. The RTGs, long cold, might have crumbled as their plutonium-238 decayed and the structural materials aged. Yet some core of the spacecraft surely remains, a twisted frame, a fragment of the golden record, something recognizable as artificial, and this remnant continues to travel. Newton's first law still holds. An object in motion remains in motion. Unless Voyager collides with something or enters a gravitational field strong enough to capture it, it will continue drifting essentially forever. Its velocity relative to the local frame is unchanged. It is an eternal traveler, a wanderer that will never stop wandering. Consider the profound loneliness of this journey. For 100 billion years, Voyager has traveled through space, surrounded by darkness, unable to see, unable to communicate, unable to know whether its message has meaning or purpose. It is the ultimate isolation, not just physical separation from other objects, but temporal separation from the era that created it. Everything that existed when Voyager launched is gone. Earth vaporized or frozen. The Sun, a cooling stellar cinder. Humanity extinct for billions of years. Even the very stars that made up the night sky have died and been replaced multiple times over. The constellations are meaningless. The galaxy is unrecognizable, yet Voyager still carries its message. The golden record still contains the sound of Anne Druyan's heartbeat, the choral movement from Beethoven's Ninth Symphony, the image of a human family, the diagram showing Earth's location in the galaxy. These patterns persist even if there is no one left who understands them, no one who speaks the languages in which they were encoded. There is something both tragic and triumphant about this. Tragic because it is a message that has no receiver, a voice calling out in a darkness that offers no response. Triumphant because, despite the darkness, despite the silence, despite the utter absence of anyone to appreciate it, the message exists. It is a fact about the universe, a small, strange fact, but a fact nonetheless. Philosophy has long grappled with the question of whether meaning requires a mind to perceive it. If a tree falls in the forest and no one hears it, does it make a sound? If Voyager carries a message through the darkness and no one receives it, does the message have meaning? Perhaps the answer is that meaning is not something conferred by reception, but something inherent in intention. Voyager was launched with intention. The golden record was created with intention, the intention to communicate, to preserve, to reach out across the cosmos. That intention, encoded in the record structure, in the spacecraft's design, persists regardless of whether it is ever understood, or perhaps meaning requires both the intention to communicate and the understanding of that communication. In that case, Voyager's meaning is suspended, potential but unrealized, waiting for a receiver who may never come. But in another sense, Voyager's meaning has already been realized by us, by humanity, by the people who built it and the people who have contemplated its journey. We are the ones who give it meaning. We are the ones who look up at the night sky, knowing that somewhere out there, beyond all the stars we can see, a small machine carries our message into the void, and we find that meaningful, not because the message will be received, but because we sent it, because we tried. Because we looked at the vast, indifferent universe and said, we want to be known. We want to leave a mark. We want our brief moment of consciousness to echo across the eons. The golden record spins silently in the darkness, waiting. It will wait for billions of years more, perhaps forever. In the darkness beyond all stars, one thing remains, a small golden echo of who we once were. Return with me now to the present moment, or something like it, a moment that still remembers Earth, that can still see the sun as more than a cooling white dwarf, where humanity's story is not yet ancient history, but ongoing narrative. Voyager 1 is out there right now. This very moment, 24 billion kilometers from home and receding, its signal still reaches us, though we know that in another decade or two, the power will finally fail, and that signal will cease. The spacecraft will continue, but silently, no longer calling home. But already, in a sense, Voyager has achieved a kind of immortality. Not the immortality of eternal function. Its instruments will fail, its systems will go dark. But the immortality of persistence, of simply continuing to exist when everything else has fallen away. We humans are transient. We live for decades, perhaps a century, if we are fortunate and healthy. Our civilizations last longer, millennia, if they are resilient and adaptive. But even our species, Homo sapiens, will not last forever. We will either go extinct, destroyed by our own hands or by natural catastrophes, or we will evolve into something different, something that would not recognize itself in us. Voyager, meanwhile, will continue. Long after the last human has died, long after Earth has been scoured by the sun's death, long after our galaxy has merged and our stars have burned out, Voyager will drift through the darkness, carrying our message. This is simultaneously humbling and empowering. Humbling because it forces us to confront our own insignificance. We are a brief flicker in the cosmos, here and gone in an evolutionary instant. But empowering because despite our insignificance, we manage to create something that transcends us, something that will outlast not just individual humans, but our entire species, our entire world. The Golden Record is not just a collection of sounds and images, it is a statement of values. By including music, we declared that aesthetic beauty matters to us, that we create art not just for utility, but for its own sake. By including greetings in multiple languages, we acknowledged our diversity and our desire to represent that diversity to others. By including natural sounds, wind, rain, birds, whales, we revealed our connection to the living world, our place in a web of biological complexity. By including human voices and heartbeats, we declared our embodied nature, the fact that we are not just abstract intelligences, but creatures of flesh and blood, born and dying on a particular world. And by launching Voyager at all, by attaching the Golden Record to it and sending it into the interstellar void, we made perhaps the most profound declaration of all, that we believe the universe is worth exploring, that we want to reach beyond ourselves, that we hope, even if we do not expect, to find others out there, and we want those others to know we existed. This is an act of extraordinary optimism. We sent Voyager knowing that the chances of it being found are vanishingly small. We knew that even if it is found, it might be billions of years in the future, long after we are gone. We knew that the finders might not understand the message, might not care about it, might find it incomprehensible or trivial, yet we sent it anyway, because the alternative, to stay silent, to leave no mark, to accept our cosmic loneliness without trying to reach out, was unacceptable. We had to try. It is part of what makes us human, this relentless curiosity, this need to explore and communicate and leave evidence of our existence. Voyager's journey is often described in metaphors of loneliness, a solitary spacecraft wandering forever through the darkness. And there is truth to this. Voyager is alone in a way that is difficult to comprehend, separated from any other human artifact by billions of kilometers, moving ever further into regions no human has seen. But there is another way to think about it. Voyager is not alone, it carries us with it. Every person whose voice is on the Golden Record travels with the spacecraft. Every musician whose work is included accompanies it into the cosmos. Every human who ever looked at the stars with wonder and hope is there, represented in the images and sounds and diagrams, and in a sense, anyone who thinks about Voyager, who contemplates its journey, who feels moved by what it represents, is traveling with it too. The spacecraft is not just a physical object, but a concept, an idea, a story we tell ourselves about who we are and what we value. That story travels not just through space, but through time, from generation to generation, changing and evolving, but maintaining its essential core. We reached for the stars. The physicist Richard Feynman once said, "The stars are made of the same atoms as the Earth." We are not separate from the cosmos, we are part of it, made of elements forged in stellar cores, animated by energy that ultimately derives from the sun, connected to everything that exists by the fundamental laws of physics. Voyager is an extension of this connection. It is matter from Earth, metals mined from our planet, elements refined and shaped and assembled, launched into space, becoming a bridge between worlds. It is us, reaching out, trying to touch the cosmos that created us, and perhaps that is enough. Perhaps it doesn't matter whether Voyager is ever found, whether its message is ever decoded, whether anyone or anything ever knows that we existed. Perhaps what matters is that we tried, that we looked at the impossible vastness of space and time, acknowledged our own tiny place within it, and still decided to send a message, because in the end, Voyager's true message is not contained in the sounds and images on the golden record. The true message is the spacecraft itself, the fact of its existence, the extraordinary accomplishment of flinging this small machine into the interstellar void. The message is, we were here. We were curious. We created beauty and knowledge and technology. We wondered about our place in the universe. We dreamed of meeting others, of being known, of transcending our biological limitations and our planetary boundaries. And we succeeded in a way that few other accomplishments in human history can match. We built something that will outlast us. We created a voice that will whisper across eternity. It became what we could never be, immortal. A voice whispering across eternity, carrying the memory of a small blue world that dared to reach for the stars. Wherever Voyager is now, whatever darkness it travels through, it carries that memory forward. It is a fragment of Earth, a shard of human consciousness, a golden echo of who we were. And in that echo, preserved against all odds, is the sound of us reaching for something greater than ourselves. This is Voyager's eternal journey, not just through space, but beyond time, beyond death, beyond the end of everything we know. And in that journey we find a kind of immortality, not for ourselves, but for what we represented, what we hoped for, what we tried to say. The journey continues, and it always will.